Today I'm going to talk about some work I've done on instability mechanisms in the equatorially trapped convectively coupled waves. This is work I've done with my supervisor Ximing. Okay, so what we've got here is a movie of the cloud top temperature. So this is a satellite record of temperature of whatever the topmost opaque object is. So here in the blue, it's where it's cold. That's looking at the tops of clouds. Where it's red and yellow, it's looking at just the ocean. And then sort of intermediate colours are medium to low clouds. Right. And if you squint really hard, you can see waves going in either direction, east and west across the equator, along the equator rather. It's really noisy. This is the problem of the real world. Okay, there's lots of stuff going on. So what we so what we can do then is we can process this data and look at where the energy is as a function of frequency and wave number. Wave number is the inverse of wavelength. And the units here are such that wave number 1 would be one wave around the whole globe. Wave number 2 would be two waves. We see several waves, several sort of regions of significant signal. There's this signal here that's called the NJO, Madden-Julian oscillation. And there's these waves here, the Kelvin waves. That's probably what I'm going to concentrate on today. There's a variety of waves. And what's drawn here are some theoretical curves for what are called shallow water waves. So if you take a tank of water that's quite large compared to its depth, and you set it rotating to simulate the rotation of the Earth, you can excite waves in the surface, and those waves have specific frequency wavelength relationships. And the fact that these waves lie on, or appear to lie on those sort of curves, inspires people to try to model these waves that way. And they share the names given to those waves. Alright, so the next movie. So this is one of these, a shallow water system being excited by a wind stress distribution. So this is a Kelvin wave coming off this way, and coming this way are what are called the Rossby waves, equatorial Rossby waves. Right, so this is what these waves look like in water. Okay, we obviously want to look at them in the atmosphere, where they're more complicated. In the atmosphere we have three-dimensional dynamics as opposed to the two-dimensional dynamics of the shallow water waves. What we can do is if you assume a sort of a fixed vertical structure, then you can project the three-dimensional equations onto two dimensions. So what we do is we assume, well, as I said, we assume vertical structures and get these various types of waves. This is what a Kelvin wave of the first mode looks like. Essentially, we have anomalously warm air in one region, anomalously cool air in another region. This is all moving to the east. Right, this is the equator. This is upwards, and then these arrows indicate the winds that those temperatures will induce. Right, so that's the first mode. There's a second mode, which is just sort of the second harmonic of that. Right, so the real waves are more complicated. Right, so this is sort of the tropopause. This is the top of the wave structure, this height here. And you see that, again, there's a lot of noise, but if you squint, or if you just trust me, this is pretty much the sum of a first mode and a second mode wave. Right, and then these waves interact with convection by sort of, in this region where there's uplift, where the air comes in and then goes up, conditions become more conducive to convection. So you get more convection here, and that pumps heat into the waves, and it moves moisture around, and in a variety of ways that can provide energy to the wave system. Either provide or take energy from the wave system. Right, so these waves are not well represented in the very complex global climate models that we use these days. You can look at the spectrum they produce, and it doesn't tend to look like reality. Right, which we think means there's something missing in their treatment of convection. So what we're trying to do is find a very simple system where we know exactly what's going on,